Hi everyone. As you just heard, my name is Leszek, and contrary to what can be seen on my badge and what is written in the agenda, I am neither employed by GSN Games, that's a printing error, and I am no longer a freelancer either. So I represent Nordic Games, and I would like to tell you about my experiences of shipping two games on Linux and SteamOS from a programmer's point of view. So just a little credibility to establish. Now I am a programmer at Nordic Games working on an unannounced project. Before that, I was a freelancer for a short period of time when I basically worked on what I continue working with Nordic Games now. And before that, I was a programmer at the Farm 51, which is basically how I ended up porting those two games in the first place. I was on the original team for both of those and then made the ports. So what will be the focus of this talk? It will not be the sales figures for Linux, because that's totally beyond my job description. It's not business viability of making games for Linux for the same reasons. I will also not bore you with game-specific bugs or the bugs that can only be attributed to my own stupidity. And regretfully, I did not... Oh, sorry. Hello, yeah, we're back. Regretfully, I did not manage to squeeze in the information about the Steam controller, but I have the controller here, so we can have a chat about it if you want. I suspect that the Steam controller part was something that could have brought some people here, so sorry for that if that's what you were hoping for. So I will talk about the platform-specific problems that I ran into and the mistakes that I made and some attempts to mitigate those problems. So the agenda. First, I will introduce short introduction of the ports, like a summary of the facts about those games. Then I will talk about getting the ball rolling on the port. The very basic building blocks of the game engine on a new platform, and then what happened after we released the ports and the feedback we got, and that will pretty much conclude the talk. So the ports, as I mentioned on one of the slides before, the games are Deathfall Adventures and Painkiller Hell and Damnation. They were developed by the Farm 51. So Painkiller is a hardcore, old-school shooter where you basically shoot monsters from hell, just as the name suggests. And Deathfall Adventures is an action-adventure game when you are Indiana Jones wannabe, basically. And the ports. So both of the games run on Unreal Engine 3. And if you think that this is a complete solution to shipping a game on every platform possible, well, that's not exactly true. And those ports that I've made, they nowadays work on all the major Linux distros, mostly work, on all the official GPU drivers, which is an important consideration on Linux. And some of the open source drivers, namely the newer AMD open source drivers. Someone might notice that Intel is also an open source driver, but it's also the official driver on Linux, the open source one for Intel graphics. Most of the middlewares that are used in Unreal Engine 3 already have Linux versions. If not already shipping with binaries, you can just get the source code and build it yourself. This is what I've done with PhysX and FaceFX and Scaleform GFX as well. Lots of X's. I also introduced some open source middlewares, namely the SDL2 boilerplate library, let's call it that. the glue library, which is an OpenGL extension wrangler. It simplifies the use of OpenGL a lot. And the Steam runtime, which is a cool collection of all the different libraries you can get on Linux. This is so that regardless of what distribution your users are running, they will get the exact same set of libraries and dependencies. So these are the things that I introduced. UE3 has its own build system, so it doesn't use Make, it doesn't use CMake or anything of the kind. It has its own Unreal build tool, which is it's written in C#, so it originally runs on .NET. Yeah, so I fixed it up to run natively, to run on Linux and compile on Linux as well. And also there is the funny content packaging cooking system. Yeah, like my T-shirt says, keep calm and cook content. So we created a Linux target for content cooking based on the existing macOS target. Yeah, so one of the things to consider is that our QA department was totally unfamiliar with Linux. So there were some very basic things that we had to train them in. Like, installing and running software, including from the command line, which is something that is very alien to many people. So file permissions, driver installations, gathering system information, those things, the driver installation and that gathering system info is now simplified a lot thanks to the facilities that the Steam client provides, because now you can just open up Steam and go to, I think it's help and then system information, something like that. So it gathers pretty complete information about the system. But the fact that they did not have a clue about Linux contributed to lots of false positives at the beginning. So I had to, that was like the biggest streak in my whole career where I closed many bugs with invalid, won't fix, and the kind. So that was a bit funny. Yeah, and also it was a spare time project over about 13 months, which means that I never worked on it full time. And I was the only programmer on the project, with occasional support from individual guys from the Farm 51. Their names are here, so kudos to them. They helped me out with a couple features, namely some rendering bugs. Yeah, so I think that's it. And you might have noticed how some of the work was based on OS X code. I think I removed one bullet point, which would have made this clear. But anyway, there is a lot of work based on existing OS X code and OS X Mac OS work, basically. And it happens all the time because it shares the standards. So there is a huge overlap area between Linux, between mobile platforms and Mac OS. Okay, on to laying the foundations. So when you start developing for a new platform, you basically, first you need to get the code to build at all. Yeah, so here's a screenshot from that fall. So the starting point we had was Epic's existing OpenGL 2.1 and OpenAL backends, which already, it was like, great, we should have something that already handles the visuals and audio. And the OpenGL mode was actually somewhat functional in Windows developer builds, because I think the OpenGL renderer was cut from the Windows release for obvious reasons. Excuse me. And there was the macOS export made by Epic themselves. And we had made some limited test builds for macOS X at the Farm 51 before. I mean, not the whole game, but things like if the menu boots up, if it runs at all, or if it crashes upon startup. So we made some very limited tests before. And at the start, the macOS binaries were built via remote compilation, which means that you had to have a Mac machine on a local network, and then the build system would transfer the source files to that machine, run the compiler on that machine, and so on and so on. So that was a bit cumbersome. And also there was the existing macOS target for game content packaging, which I had used in the beginning for Linux packaging as well. I mean, I just renamed the directory from cooked Mac to cook Linux, whatever, and it worked initially. But both of those ports were somewhat unfinished, and if you ask someone who had actually tried shipping a macOS title on UE3, they will tell you some horror stories. Heck, I will tell you some horror stories. And also, one fact which is of note is that on Windows, both games have had only 32-bit binaries. Yeah, because it seemed that 64-bit binaries are not necessary. They turned out to be on Linux, at least in some cases. Okay, so first, building the build tool. So I started with patching Unreal Build 2 so that it can run on Linux, because I thought that just having to have 2 machines just to build the code was not very comfortable, especially as I spent most of my time development time on Linux for obvious reasons. So I decided to make an effort and port it anyway, even though Ryan Gordon, who is the legendary porter for Linux games, he recommended actually dropping UBT and writing a CMake file instead. I did not follow this advice because it didn't seem right to me, especially having experience with UBT and knowing more or less how it works. It seemed to me that it's kind of simple. So why shouldn't I be able to port it? And I did port it, and it was quite easy. I just added the support for Linux toolchains. The UBT has a pretty nice structure for adding new platforms, so that was quite easy. I also fixed the hard coding of backslashes in paths, which is also an obvious mistake when writing predominantly Windows code. This is easily fixed by using the path join method. And the only real issue that I ran into was the overflowing of stack when UBT was trying to find dependencies in C++ sources, like following includes and the like. So that was blowing up the stack. So I basically had to break up the string into smaller parts of, I think, 5,000 characters or something like that. Of course, considering the new lines and so on, but it worked, and it does work. Yeah, and after that, I had a 64-bit developer machine, and I think that 32 bits should die already. But we cannot be. I wasn't allowed to kill it on this because I had to assume that if the game runs on a hardware configuration on Windows, it should also be able to run on the same hardware configuration on Linux. So yeah, so I basically had to do cross-compiling for 32 bits from 64. And initially, I had a separate ch root, which is it's a Unix thing. It's kind of like a virtual machine, but which uses the same system kernel. But that didn't work very well. So yeah, so calling the compiler with the M32 or M64 switch is not enough, because this only sets the machine code generation. And this does not handle the headers and libraries, so you will not have the Steam runtime in the correct bitness, you won't have OpenMP if you use it, or libgcc, which is a collection of some low-level routines that GCC uses. So on Debian and Friends, this is fixed by installing a package called GCC multilib. There's also a similar package for other distributions, so if you're having problems building 32-bit libraries or 64-bit libraries on a 32-bit system, then you might want to check this out. Yeah, and also Clang. Clang is recently being, reiterated ad nauseum. So you might be fed up with people advertising Clang already, but I have to do this anyway. because it's faster. So if you're trying to do quick iterations, it's an obvious win. It has different diagnostic than GCC. Here are some like here's a comparison of time, of build times of the same project, of 1 million lines of code project on my current machine, which is a Xeon quad-core CPU. The Clang also is C++ preprocessor compatible with GCC. So most code that works in GCC will also work in Clang. It also has command line compatibility for the most part with GCC, which means that you can just easily switch back and forth between Clang and GCC. And this is very good. This is very good because having your sources verified by 2 different compilers can help you catch some subtle bugs. But of course, Clang is not a solution for everything. And some of the caveats include that object files may be incompatible with GCC. It has generated different mangled symbols for the same symbols than GCC for me. So sometimes you need a full rebuild. And GCC is also more mature than Clang. It actually happened to me that Clang has generated faulty code, so which was just behaving incorrectly. But your mileage may vary. So it might happen to you, it might not. It's still worth a try. There are some slight inconsistencies between how GCC and Clang handles some standards, C++ standards strictness. So you may need to add this and the arrow in some places or name some anonymous types, but it's nothing serious. So Clang or GCC, I actually used both for this. So Clang was used for quick iterations during development and GCC for final shipping libraries. And then after building all the objects, you have to link them. So the default linker on Linux is the GNU LD, and it's ancient and it's single-threaded, and it requires you to specify the libraries in the order of reverse dependency. So basically, you first need to specify the objects of your program, and then the libraries that your program uses, and in such an order that you first include the library that needs symbols from the later libraries. So it's not very intuitive. It really gets annoying when I have a circular dependency, like for instance with some physics libraries. You have some one library which depends on the other, and that other library also depends on the first one. But we are not doomed to use it. I highly recommend to use the GNU Gold linker, which is a multi-threaded linker developed at Google. It's now officially part of the GNU utils. It's very fast. For this project, which compiled for 3 minutes and something, this gives me an over 3 times speed up, so it's very good for quick iterations. And it's a totally drop-in replacement for LD as long as you use C and C++ code. You may need to give an additional parameter to your toolchain setup to use it, but it's not a game breaker or anything. It still needs the libs in the order of reference dependency, but this can be easily remedied by using the library groups. I mean, the proper way of specifying dependencies for LD is to, if you have circular dependencies, is to re-specify the library again. And I think that sucks, and I prefer to actually use the library groups, which means that this is the G++ syntax with the -WL syntax for forwarding parameters to the linker. So basically, I wrap all the libraries that my binary uses in those bracket thing, and this causes an exhaustive symbol search within the library group, which the manual warns that it may hit your performance, but I haven't noticed it. I mean, so it's possible that it will kill the performance of linking, so keep that in mind, but I haven't observed it. So who knows? And also, the one thing that I found very frustrating at the beginning was that the debugging symbols, which were huge, it's like you had 300 megabytes of PDB files in in a Windows build from Visual Studio. That's really a lot. And when you try to load your binary in GDB, on every GDB startup, it takes several minutes to process. So that's really annoying and wastes a lot of time. What GDB actually does then is that it parses those hundreds of megabytes of symbol files to create a quick lookup data structure. So I think it only makes sense to try to cache it and fold it into the build process, which can be quite easily done if you have some basic shell script support in your build system. If you download the slides, this is a link, so you can click it and go directly to the GDB manual. But it's basically this. You basically open the freshly built binary in GDB, and you tell it to cache the GDB index into a directory, and then you use the object copy tool to integrate this index into your binary, and it works. And then all this, when you strip the binary, this GDB index gets stripped as well, so it does not bloat your binary if you're afraid of that. And then after you have your code building, you probably want to have some boilerplate running. So I initially tried rolling my own boilerplate using row X11 client calls. And basic events for the input, for windowing, that's pretty easy. But then you try to get Unicode text input, and it stops being easy. Then when you try to do, borderless full screen and so on, it gets even worse. So it's not easy. It's hopeless spaghetti of code that you really don't want in your engine. It's the same with joystick API, because you have to use low-level IOCTL APIs to access the block device. It might be that different distros have the joystick block device under a different path, under /dev. So it's a headache, and I recommend not doing that, and instead using SDL. Above all, X11 seems to be on its way out, which means that it's basically an ancient system. X-Windows system was developed in, 1970s or something like that? So this is the 11th revision of that protocol, which has been around since the 1990s, I think. So it's still quite old. And it's mostly a network protocol. And there is a group of researchers who have now started running static analysis on the code of X11, and they have found over 1,000 vulnerabilities. So it's really a mess, and there is a lot of pressure from the Linux desktop community to push X11 out of the way and replace it with Wayland or Mir, depending on the distribution, because for whatever reason, Canonical wants to have their own display windowing system in Ubuntu. But anyway, so if you use SDL, you're covered. If they even make the switch, SDL will handle that for you. The interface that your engine sees does not change. So I think that's some good value in this. And if you want to learn about some other benefits of using SDL2, there is also a link to my talk from another Polish conference from last year, where I talked about that exactly. And that concludes the foundation laying part. And now on to what happened at the release and the feedback that we received. Yeah, that's a screenshot from Pinkler. What we shipped initially with the beta was that we also had only 32-bit libraries. 64-bit libraries were added later on. We have about 20 lines of launch script, which basically only detects the architecture that the game is being launched on, meaning 32 or 64 bits. Initially, it only had a stub for launching the 64-bit binary for obvious reasons, so it fell back to 32-bit anyway. It also injects the Steam runtime if it's not already present, because I've found that some users will go to extreme lengths to try to screw up your installation. So I try to I tried to sidestep that by explicitly injecting the Steam runtime anyway. And that's about it. So we haven't shipped any additional dependency. We haven't shipped SDL or anything. Just we said that we want this game on Steam runtime, and that's it. Because this allows us to shift some responsibility on having the dependencies working to Valve. Well, obviously, this is the condition is that you are shipping a game on Steam, but it still should be quite easy to cut out the elements of Steam runtime that you need for your own game. If that happens, it's just that then you need to do some licensing paperwork, host the source code somewhere, and so on. So it's, you know, if you are shipping on Steam and you can use Steam runtime, use it, because it just saves you lots of headaches. Yeah, this also allows us to tell the users that insist on doing their own thing that, yeah, well, we are not taking responsibility for you tampering with your system, because this happens, and yeah, well. Yeah, and the feedback that we started receiving, I will not, of course, bore you with all the details and all the crash reports and whatnot, but yeah, so as I just said, at first there were lots of missing incompatible libraries reports. That was mostly because people were disabling the Steam runtime. And it was mostly the users of Gen 2. It's well, it's a distro of Linux where you build everything by yourself. So you build everything from source code. So those people they usually have an agenda, and they insist on using their own instead of the Steam runtime. And in fact, the maintainer of the Steam package for Gen 2 had chosen to disable it by default. He's changed it since then, but it generated quite a few problems for us. This is fixed by telling people to run Steam like this. So we just tell them to inject the Steam runtime equals 1 environmental variable, and that's it. It also happened quite frequently that people were missing, in quotes, because they were not really missing them, the 32-bit OpenGL libraries on NVIDIA drivers on 64-bit systems, because they might end up being installed to a path where the dynamic linker cannot find them. For example, this is the case on, I think at least it was on Ubuntu, because our QA reported this, and I initially dismissed it as resulting from the lack of experience, but then found out that they were actually right, that those libraries were not in the search path. So I added user lib32 to the launch script to the library path, and that fixed it. Also, it sometimes happened that people installed the drivers and did not install the 32-bit library, so it's an option. So it's good to put in the README or something that if you're shipping 32-bit binaries, just maybe tell them that they should make sure they are installing the compatibility 32-bit libraries. What was also a frequent problem is that even on hardware which was capable of this feature, there was no support for DXT textures. And I mean, this doesn't make sense, but after some research, it turned out that this concerns the open source drivers, and I think VIA acquired those patents from S3. They have patents on this DXT texture compression. Basically, if you are using the using the decoder for those textures, you need to pay them a licensing fee. So some of the more radical open source projects will not ship support for those textures. Fedora is one. And if so what I did is that if the extension is not advertised by driver, because it's required, so I cannot just sidestep it, I'm quitting the game and suggesting the user to install this package. It's usually a distro package, so there is no huge hassle, and this helped some users, in my experience. Yeah, we also had a ton of other issues, which I will not delve into because, frankly, most of them were because I'm stupid. And yeah, but those two things I'm going to cover with a little bit more detail. Yeah, crashes. So when you have crashes, you need to, and you have them in the wild on production, you need to be able to somehow find the source. So in Linux, crash handlers are actually signal handlers. Signals are an asynchronous inter-process communication mechanism. It's also a bit ancient. It's from Unix. It's standardized in the POSIX ISO standard. The source of the signal can be the process itself, or the other processes, or the kernel. So, for example, if you try to read from an unmapped range of virtual memory, you will get a signal from the kernel. And you can specify custom handlers for those signals, because the default one will most likely terminate the process and dump the core, which is a bit like mini dump on Windows. So it's a dump of memory, basically. I wrote here that you must specify custom handlers. Well, it's not such a strong must, but it's highly recommended, because then you really get some additional control and additional information. So there is this sig action system call, which sets signal handlers. There is a very, very good talk about writing application fault handlers for Linux. This is also a link in the slides, so you can click it once you download it. So yeah, so if you look at this signature, you will get a siginfo-t structure, a pointer to one, which has some like 20 fields or something about this, but there are a few which are particularly interesting. You can get the error number value, the Unix errno code, an additional code which specifies the reasons for sending the signal. And the reasons can be both general and per signal type. So for instance, you can, this way you can know if the signal was sent by a user or by the kernel, or if it was because of, or if you get a segmentation fault, what was the reason? If it was an illegal addressing mode, or invalid permissions, or the address was unmapped, or if you had a floating point overflow, underflow, whatever. So it gives you more detailed information about the source of the signal. And some of the signals are related, I mean, they are associated with some memory address, like illegal instruction or the segmentation fault, so you will also get this address in some of the signals. But it's very easy to use those signal handlers. It's very difficult to do it right. So for instance, it's not safe to allocate a free heap memory, because it might have the control data structures for malloc and free may have been corrupted in default. There is also a lot of surface area for race condition problems. So you can, for instance, share locks with the main program, because if a resource is locked and you get a signal, then the code that was locking is interrupted regardless, no matter what. So you will get a deadlock. And also there are some Unix specific things that you cannot do with system calls. So there is a list of async unsafe functions. For instance, you cannot call print, which sucks. I mean, you shouldn't, because if you call print, it usually works anyway. But it's just not safe, so keep that in mind. And the custom handlers do not dump core, which means that you will not get the memory dump, which you might want. So if you want to dump core anyway, you can just restore the default handler after your own by calling signal, the code for the signal, and then this constant called sigdfl. And then re-signal your own process. And then you will get the core dump. So if you want to walk the stack safely, there is glibc provides, which is the C library that Linux usually uses. It provides a backtrace function, which does just that. It walks the stack and puts the addresses that it finds in the return, in the IP, in the pointers, in an array. And the symbols are read from the dynamic symbol table of the binary, which means that you must pass a parameter like this, -r dynamic, to GCC or Clang when you build, because otherwise you will get some missing symbols in the backtrace. And calling backtrace symbols allocates heap memory, so it's not safe. It's the function that that translates actually translates the addresses to symbols. Still, you can get away with it most of the time. So, you know, I took the risk. I did not implement the proper solution, which involves, you know, like forking at the start of the process just to have a watchdog process separately, you know, working in the background and piping information to it instead, and so on. So I took the risk. I am calling backtrace symbols, and it works 99.9% of the time. So your mileage may vary, but from my experience, I mean, I can recall one or maybe two cases where the output of backtrace symbol was broken. So you might be more prone to this if you were using an embedded system, but on a you know, in a full-blown PC, I don't think this usually happens. Yeah, and then there were the long load times and the unresponsiveness of the game. This was the biggest problem of the entire port, and to this day it remains only partially solved. I am no longer on this project, which is why I am not trying to fix it right now. Anyway, so profiling quickly places the blame on linking the GLSL shaders, because the OpenGL shader mode operates on program objects and not separate shaders. When you compile the shaders, they need to be linked together before they can be used as a combination. So this introduces a lot of redundancy. If you just compare the parameters you can get in the GL-get program and GL-get shader OpenGL calls, you will see that there is a huge overlap in the information that you can get from both, and I'm pretty sure that this information is not calculated upon request. I think that it should be cached, or the driver implementers would risk in compliance with the OpenGL spec. So, so that's one bad thing about this. Another one is that drivers often actually defer the actual compilation until you try to link those shaders. So they do some, when you compile the shader, it does some preliminary syntax checks, but it doesn't actually generate the code yet. The reason is that in OpenGL, you can have, by default, you have automatic assignment of what is called vertex streams in Direct3D, which is the vertex attribute streams, and you know, so varying variables and uniforms, all of this. No, they are not explicitly. I mean, there is an extension in newer OpenGL to explicitly tell the driver where to locate the different data, but by default, this is done automatically. And the UE3 renderer uses OpenGL 2.1 when you can only do it automatic unless the extension is present, and we cannot count that the extension is present. So this also leads to, as I said, this redundancy also leads to increased memory consumption, which is why I decided to ship 64-bit binaries at some point. Yeah, because basically the drivers were causing the game to run out of virtual address space, which is something I had never expected, but it did happen. Yeah, and the thing that really sucked is that OpenGL renderer of the Unreal Engine 3, it blocks the render thread when it links the shaders. So, you know, if this happened on the render thread when the loading screen was on, then this caused the loading screen to freeze. And yeah, you know, you can imagine that this is very frustrating. And what's even worse, it caused asynchronous level streaming to do exactly the same. So you would have the level streaming in the background, and the game would still stutter, even though it's asynchronous and theoretically in the background. So this sucked very badly. And also, it doesn't help that the games both have thousands of shaders, like 15,000 or something. So that creates an awful lot of vertex and fragment shader combinations. So that's really blew my head off. Yeah. Okay. Thanks. We're almost at the end. And it's better. The situation was better on subsequent loads on NVIDIA because the driver implements a cache of shaders of its own. Yeah, so the short-term fix that I implemented was to move the shader linking to the background, which is it's a hack, basically, because I just create a worker thread with a separate OpenGL context. It shares data with the main one, and in principle, I never synchronously link the shaders anymore. I just queue the jobs to execute on the worker. And if on a loading screen, I keep spinning the loading screen until the shaders are done. And the same with the async streaming done notifications. So I just do not call the notification until the shader link queue is empty. So this was quick and easy to implement and fixes the gameplay stuttering, but it does not fix the long load times. So it's not even a fix, it's a hack. And more than that, it was a disaster on the official AMD Catalyst driver because it caused a total system hang. The PC needs a hard reset. I was in touch with AMD about this, and apparently we've exposed the erased condition in the driver, which they have acknowledged, and then they kept telling me, yeah, we will fix it in the next release, and they still haven't fixed it yet. So I don't know what's going on with them. I kind of gave up hope that they will fix it. So I basically added a fallback to the old blocking code path if Catalyst detected, so we basically have a worse user experience on that platform because they are not willing to fix the race condition in the driver. Yeah, but there is a possible improvement suggested by Epic to use the separate shader objects extension. This kind of switches the shader model into a more direct 3D-like model. It removes a lot of redundancy because it replaces programs and linking with much lighter pipeline objects. And it will also play well with the architecture of the UE3 renderer, which is modeled mostly after D3D. But I haven't implemented it because I didn't have the time to do it. And it basically would require a shader syntax upgrade because UE3 uses GLSL 1.2, where I would need at least 1.4, which was the version released with OpenGL 3.1. Mostly because it requires explicit locations for attributes and varying. So that's what I was saying. And like the very proper fix would be to defer access to the shader objects. I've talked to some NVIDIA guys about this as well. That modern drivers just queue shader compiles on a separate thread, and then process those job requests in a multi-threaded manner. So recently, the open source Mesa drivers in SteamOS have got this as well, because they previously didn't do that. Those changes are now being integrated into upstream Mesa, so I guess the next release will already have them. So basically, the mode of operation that you should assume is that you kick all the jobs at level load, even if you don't need the shader right now. Just like we will need the shader in the future, so just compile it already in the background. But you do not access all the objects, any of the objects. You do not query even if they compiled all right or anything. You just don't access them. You just kick the jobs and move on, and then only access them until when they are needed. So because if you request information about those objects, you are creating a synchronization point. So the driver will have to empty the queue of the shaders waiting for compilation until at least this object that you are trying to access. So also, I did not implement this because it would also require a considerable refactor of the UE3 renderer. Yeah, but it's the proper solution. Valve has recently already also shipped that in Dota 2 on Linux. So yeah, so all the big three IHVs they suggest we should do that. And it's time for the summary. Yeah, so just a quick reiteration of the points. Porting .NET-based tools to Linux is definitely viable, as long as I don't use any graphics user interface things. Cross-compile, bitness cross-compile issues are solved with GCC multilib, mostly. Not all of them, but most of them. Switching back and forth between Clang and GCC is easy and useful. Use Gold for linking because it's multi-threaded. Cache the GDB index because it improves your own debugging experience. And SDL2 is way, way better than rolling your own boilerplate. Yeah, Steam runtime is also good for you. Crash handling in easy crash handling in Linux, easy to do, tricky to get right. Shader modal. Linking is slow. That's the the main point of that part. And multiple concurrent OpenGL contexts can still bite you. Like this thing that we had, this issue that we had with AMD was precisely because of this multiple concurrent OpenGL objects contexts. Yeah, and like the reason why it has bitten us is because we did not really test on different GPU drivers. So it's very good to do that. And if there are questions, then please.
I think we have a really short time for questions. So yeah.
So I have a really quick question about the build process. So how many libraries do you provide by yourself along with the binary, and what is the total file size?
You mean the external dependency, the third party, or what's inside the engine?
Everything apart from the engine code itself.
Well, I cannot really remember for UE3, but with my current project, which is also a AAA, I have like 30 different libraries. And actually those stats, the 3 minutes and so on, were not from UE3, but from my current project. But it's a similarly sized code base. And there were like 30 third-party libraries. And well, the resulting binary, before stripping the debug symbols, is 300 megabytes. So that's big.
All right.
Here's one.
One question, because you mentioned two problems that you had, one with catching those signals and whatnot, and have you considered using Breakpad? I believe it's a Google application, Google, if this works. I don't know, what's your opinion on this? Yes,
I have, but I was kind of tight schedule, and I did not really want to go around and implement all the middlewares and so on. I mean, it probably could, from what I've read, it would be useful, but I just didn't do that because of reasons. Mm-hmm. So sorry, I cannot really give you a satisfactory explanation.
I just wanted to know if it worked for you or not. And the last question: were there any efficiency problems that you had? I mean, the performance of the game was much worse. It was similar.
No, it was totally on par with performance on Windows, at least on NVIDIA. So once the shaders are cached, there really is nothing to complain about. It's pretty solid.
Okay, thank you.
And last questions? So thank you very much, Leszek, for your presentation.
Thank you very much.